Hello everybody. Today's topic is the features of waves. Yesterday we took a look at what waves are, how we can define waves, and the different types of waves. Today we're going a little bit deeper into our unit on waves, and we're taking a look at what are waves made of and which one is faster, sound or light waves. So this is our essential question for today, and we are going to talk about this as we move through these notes. So keep that in mind. Which wave is faster, sound or light waves? All right, let's move on into our notes. Okay, our first section we have here is the features of waves. The first features of waves we have are the different parts of a wave. So we can see here that transverse waves have crests, which are the highest points, and troughs, which are the lowest points of a wave. And we've already established this, but it's nice to have the description right beside a picture like this. So this is a transverse wave. A transverse wave, remember, it traverses or crosses this equilibrium position or resting position. And in a transverse wave, the top part of the wave here is called a crest. And then the lower part down here is called a trough. So here's a crest, here's a crest, here's a crest. Then we've got down here a trough and a trough. Okay? Moving on to a compressional wave. Compressional waves, remember, have compressions and refractions. And compressional waves have dense regions, which if we use this spring here as an example of showing us compressional waves, we see that the coils are close together. Those are the areas of where the matter is the densest. It's like squished together the most. And the less dense regions are called refractions. So here where it's squished together, that's a compression. And where it's relaxed, that's a rarefaction. Okay? We got another compression, and we have another rarefaction right here. And that's the one that's labeled. Okay, so these are the different parts of compressional waves and transverse waves. Okay, our next section is all about wavelength. Wavelength, it's represented by this strange symbol. It's called the Greek letter lambda. Lambda represents wavelength, and by definition, wavelength is the distance between one point on a wave and a similar point nearest to it. For example, a wavelength could be from crest to crest, or it could be from trough to trough, or if we were looking at a compressional wave instead of a transverse wave, it would be the distance between compressions, or the distance from rarefaction to rarefaction. Okay? And down here at the bottom we have this relationship. A wavelength of a wave decreases as frequency increases. So here in just a moment we're going to discuss frequency, and then we're going to look at the comparison of wavelength and frequency as they're related in terms of wave speed. Alright, so here's frequency. Frequency is represented by the letter F, F for frequency. And this is the number of wavelengths that pass a fixed point each second. And frequency is measured in hertz, and that's represented by an Hz. Okay? So frequency is the number of things, or number of wavelengths rather, that pass a certain point each second. All right? And on the previous slide, we said that, I'll go back to it, we said that the wavelength of a wave decreases as frequency increases. So as one goes up, the other goes down. We can say that wavelength and frequency are inversely proportional. As one goes up, the other goes down. So they're inversely proportional. For those of you who are in algebra, you might have to use that terminology. They're inversely proportional. Okay, so if we were wanting to calculate the speed of a wave, now remember back when we covered speed and acceleration and velocity and stuff, we represented speed with the letter V, and wave speed, just like any other speed, is measured in meters per second. Okay? And to calculate the speed of a wave, we multiply the frequency, F, in hertz, times the wavelength, which is represented by lambda, in meters. And you may be thinking to yourself, well, how does hertz times meters become meters per second? Well, if you look up here in the definition, we see that frequency is the number of wavelengths that pass a point every second. So hertz is actually saying the number per second, all right? So if we have per second times meters, we end up with meters per second. And that's an easy way to remember how to calculate wave speed. And just remember, if you have the same type of wave speed for a wave that you're comparing, and you notice that the frequency goes down, then the wavelength has to go up, okay? Because frequency and wavelength are inversely proportional, okay? All right, we're going to take a look at our next topic, which is amplitude. Amplitude, by definition, is a measure of the energy in a wave. And we can see here that the more energy a wave carries, the greater the amplitude. And closer to the definition of amplitude we've got here is amplitude is the distance in a transverse wave from crest to the normal position or the trough to the normal position in a transverse wave. Now, what the normal position is kind of that equilibrium position that runs right down the middle of the wave, or the resting position. Now, the denser the compression, or the more squished together the particles of that medium are, the larger the amplitude in a compressional wave. Okay, so that has to do with how much energy is in there. So for a transverse wave, if we're seeing these really high peaks and low troughs, we can say that that has higher amplitude compared to one that has these, smaller little rolling peaks and troughs. That has a lower amplitude. It's related to the amount of energy in that wave. So this wave up here would be the higher energy wave because it has higher amplitude, and this one would be lower energy. Then this comparison with the compressional waves, we can see here that the particles are closer together in these compressions. See how there's this empty space out here in the rarefaction? Now this means that there is a higher amplitude. There is more energy in this wave right here compared to this bottom one. And this lower amplitude wave, we see that there is a compression for sure, but the particles are still kind of distributed in that lower, in that rarefaction portion, in the relaxed portion. Okay, so that finishes our notes for today. I do want to go back to our essential question. Which is faster, sound or light waves? Well, yesterday, remember, we established that a sound wave was a compressional wave, and light waves can travel without a medium. So you guys tell me, which one's faster, sound or light? Okay, discuss that with your shoulder partner, come up with an answer, ask Mrs. Parson or Mrs. Witt if that is correct, and then we're going to move back to the lab tables and work on our activity for today. All right, have a good one.